All right, example 17, which is our last example that we're working on for graphing tan functions. Let's have a look at what we've got. So y equals 3 tan 2x minus pi on 3, and we're graphing from 0 to 2 pi. So let's start with our period. That's going to be pi over our n value, which is 2. We're not reflected at all, okay, but we do have a horizontal translation, and so that's going to affect our asymptotes. So what we do is now we write 2x minus pi on 3 is equal to our normal asymptotes, which is going to be, now we're going from 0 to 2 pi, so we'll just do positive only, pi on 2, and then 3 pi on 2, and then 5 pi on 2, and we'll do another one here, 7 pi on 2. Now what we need to do is solve each of these for x. So first things first, we need to add pi on 3 to each of these. So 2x equals pi on 2 plus pi on 3. Okay, so now we've got different denominators here. You could just, on your calculator if you like, ignoring the pi, 1/2 plus 1/3, and add them together. Of course, if you're in the non-calculator section of a test, then you need to be able to do it without a calculator, and you should be able to do it without a calculator. That will become 3 pi over 6 plus 2 pi over 6, so that's 5 pi over 6. This is going to be 3 3s are 9 plus 2 is 11 pi over 6. 3 5s are 15 plus 2 is 17 pi over 6. And then 7 3s are 21 plus 2 is 23 pi over 6. And now we need to divide each of these by 2. So x will be 5 pi on 12, 11 pi on 12, 17 pi on 12, and 23 pi on 12. So that's where our asymptotes are going to be. All right, so here we've got our axes. We're going from 0 to 2 pi. So we're going to mark in our end there at 2 pi. And how do we fill out the rest of the scale? Well, because our asymptotes are in twelfths, we really probably should be dividing it up into 12, well, from 0 to pi in 12. So if we put pi here, this is going to be divided up into 12 parts. Okay, now that's a lot. Okay, so probably what we'll do is we'll mark it, but we'll only label the relevant ones. Okay, so because it's in 12, that's going to be useful if we make that there, and then we can divide this up into 6, which means put there, which means dividing that up into 3. So it just makes it a bit easier. So that's thirds. That's now sixths. Okay, now our first asymptote, I'll do the rest as well. Okay, so that's what we've got. Now, first asymptote here is 5 pi on 12. So that's 1, 2, 3, 4, 5 pi on 12. So that point there is our asymptote. Then we've next one's at 11. So that's 6, 7, 8, 9, 10, 11, pi on 12. So I might just erase my pi. So where are we? 6, 7, 8, 9, 10, 11. And 12. Next one's at 17. So that's 12, 13, 14, 15, 16, 17. And then the last one at 23, which will be there. Which, because of that 2 pi, don't worry about it. I'll just link to it. So that's 23 pi on 12. All right, so marking in our asymptotes. Okay, so we've got our asymptotes there, and pi on 2 radians, so that makes sense because we're going from 5 to 11. That's 6 pi on 12, which is pi on 2. So we can see here that our last asymptote is just before the 2 pi. Now we know that our period is every pi on 2 units. The next one back this way actually would be here. Okay, at negative pi on 12. Just going to mark that in because this is just to help us to identify where our axis intercepts are. Okay, the axis intercepts, because there's no vertical translation, it's going to be halfway between our asymptotes. So halfway between here and here, that's 1, 2, 3. It's going to be right there. Next one will be 2, 3. Next one here, and then here as well. So we'll label those. So what have we got? These are every pi on 12. So that's 1 pi on 12, 2 pi on 12, which is pi on 6. This is 5, 6, 7, 8 pi on 12, which is going to be 2 pi on 3. 12, 13, 14 pi on 12, which is 7 pi on 6. And then 18, 19, 20, 20 pi on 12, which is 10 pi on 6, which is 5 pi on 3. Okay, so that's where our intercepts are. And we can go like that, there, 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 and there. So we're going to have an endpoint somewhere here. This actually is going to be an endpoint there as well. Well, it's probably down here actually, somewhere. Not this bit here. That's probably, no, it's too big. All right, let's just have to ignore that bit there. Okay, so what we need to do, because we need to label our endpoints as well, work out what these endpoints are. So that's where our, so if we, this point here and this point here will have the same y value. Okay, let's work out what that is then. here's when x equals 0, which will be nice and convenient. So if x equals 0, then y is going to be 3 tan 2 times 0 minus pi on 3, which is 3 tan negative pi on 3, and tan of negative pi on 3 negative pi on 3 is down here, which would be the negative value of pi on 3, which would be up here. And according to our information table, tan of pi on 3 is going to be root 3. So that's 3 times root 3, but of course it's negative. So negative 3 root 3 is our value. So that endpoint there is going to be 0, negative 3 root 3. This one here will be 2 pi, negative 3 root 3. Okay, you can check that on your CAS calculator and you'll find that's the case. Okay, so we've got our endpoints, we've got our asymptotes and our intercepts here. The only other thing which would be worthwhile mentioning is that, now they haven't done an example here, but if there was an example where you also got a vertical translation, okay, you also want to be able to identify your intercepts, but also where that point of inflection is. Okay, now the point of inflection is where the shape changes from being concave down to concave up. It's that sort of halfway point where it starts to curve in the other direction. Okay, and if we've got a vertical translation, then it's going to be either up or down, so you need to label that as well.